Hello guys, welcome to my YouTube channel or the Big Structural Hub. So this is a place where you learn, build and innovate. So today I want to solve problem number 2 under 3-moment theorem. And this is the question. It is a question from NEC past paper, that is October-November 2014, structure 3. So the question says, a beam ABC is built in at A and C and supported on rollers at B as shown in the figure below. Analyze the beam using 3-moment theorem and draw the bending moment diagram indicating all critical values. So the question carries 20 marks. So this is the beam. As you can see, this is the beam. It is a continuous beam. It has a point load of 10 kilonewton and a UDL of 10 kilonewton per meter. So let's see how we can solve such a problem. So the first thing to do for this one, you'll assume an imaginary span at A, at point A, and also at C. So let's assume an imaginary span. So let's call it O1. And then also we assume an imaginary span on the other side and call it O2, like that. So the reason as why you are assuming an imaginary span is because we will have moment at point A and at point C. So we will have to consider span OA and AB so that you can find moment at A and also at C. So after doing so, you can extend the line to create a space to draw the diagram required. So extend those lines and make sure you are doing it on one page, not separate pages. So like that. After doing so, you can as well extend this one and also this one. So like that. After having done so, the next thing is to start solving the problem. So solution. Solution. The first thing to do is to calculate free span bending moment. So free span moments. So consider each span as a simply supported span. For example, span AB, span AB. As you can see, span AB, it has an eccentric load of 20 kilonewton. So M max, the maximum bending moment for an eccentric simply supported beam is WAB over L. So this one will be 20 times 2 times 3 over 5. So this is L, 2 plus 3, 5. So it will give you 24 kilonewton meter. 24 kilonewton meter. So we go to the next span, span BC. Span BC, we consider it as a simply supported beam. So it has a UDL. So the maximum moment for that will be WL squared over 8. So WL squared over 8. So this one will be 10 times L, which is 4 square over 8. So this one will give you 20 kilonewton meter. Like that. So after doing so, the next thing is to draw free body diagram moment. So we'll draw our free body moment diagram here. So span AB is 24. So this one is 24. It's a rectangle. So our H is 24. And BC is 20 kilonewton meter. So somewhere like there. So our H will be 20. So after doing so, the next thing to do is to apply the three moment theorem formula. So for this one, we will use the second formula because our EI or I is not constant. Our EI is varying. For example, you have 2I and I. So apply three moment theorem formula. And how do you apply? For you to apply three moment theorem, you need to consider two consecutive span. And for our case, we begin from here by considering two consecutive span going to the other side. So we have to consider span O1, A and AB. So this is our span. So span O1A, AB. So that is our two consecutive span. After doing so, now write the formula for this span. So our formula will be M O1 LO IO because our length here is LO. Let's say LO because it is an imaginary span. Again, our I is 0 because it's an imaginary span. So plus 2 MA into bracket LO IO L0 I0 not O plus L1 I1 plus MB, this one, L1 I1 is equal to minus 6 into bracket A0 x bar 0 over L0 I0 plus A1 x bar 1 L1 I1. Like that, we have our formula. So we have taken this A0 x bar 0 L0 I0 because there is no any geometric figure as a result of free span moment at this side, because we have assumed an imaginary span. So that's why we have A0 x bar 0 over L0 I0. So we proceed. Having done so, you can say but L0 is equal to I0 is equal to A0 is equal to x bar 0 is equal to what again? Yeah, so it's equal to 0. So we can eliminate some values in this equation as a result of 0. So this one will be 0. So the equation will be 2 ma. This one will be again 0 into bracket L1 I1 plus MB L1 I1. This one A0 x bar 0 will be 0. So the whole of this will be 0. So it will be equals to minus 6 A1 x bar 1 L1 I1. So that is our final formula. So after having done so, we have 2ma into bracket L1 I1 plus MB L1 I1 is equal to minus 6 A1 x bar 1 over L1. So this is our formula, our final formula. Now we calculate A1 x bar 1. So this one is the area of this one, of this shape, which is a triangle, and then you multiply by its centroid, which is x bar. So the area is a half length times width, a half length times height. So it is a half length, that is 2 plus 3, 5. And then times the h is 24 times the centroid. The centroid, you can use this formula, b plus 3, b plus l over 3. So this one will be a half times 5 times 24 times into bracket. So something to note, when you are calculating, or when you want to find the centroid, you will consider the common joints. So the common joint here is A. It's a common joint because it's sharing span LO and span L1. So this is span L1. This is L2. So it's a common joint. So it is sharing the two span. So the section which is so close to a common joint is A, and the remaining one is B. So our B will be 3 plus L, which is 5 over 3, like that. So the answer will be 160. That is it. After doing so, we can insert known values to the equation. So we have L1, I1. L1 is 5 over I, which is 2, times 2, MA, plus L1 is 5 again over 2, MB. This one should be give you minus 6 into bracket 160 over 5 times 2. So A1, X bar 1 is 160, and then L1 is 5, I1 is 2, like that. So we'll end up having 5 MA plus 2.5 MB should be equal to minus 96. So this is equation 1. We call it equation 1. After that, we go again to the next two consecutive span. So the next two consecutive span, it will be span AB, span BC. So consider span AB, BC for the three-moment theorem to apply. So if we can write the three-moment theorem based on this span, we'll have MA, L1, I1 plus 2 MB, we have 2 MB into bracket L1, I1 plus L2, I2 plus MC, L2, I2. It should be equal to minus 6 into bracket A1, X bar 1, L1, I1 plus A2, X bar 2, L2, I2. Like that. Again, we will start calculating our areas and centroid of the respective geometric figures. We have this one and this one. So for A1, A1 X bar 1 will be the area of this one times its centroid. So the area will be a half times 5 times 24 times B plus L over 3. Like that. That is the formula for centroid. So this one will be a half times 5 times 24 times B. Now, our common joint here is B. Our common joint here is B, meaning our A, it now changes. Our A is this one, and our B is that one. So you can see the difference. Something very important to note is a common joint. So a section which is so close to a common joint is A, this section. is A, and then the remaining one is B. So it will be 2 plus L, which is 5, over 3. So this one will give you, uh, 140, like that. And then we proceed to A2, x bar 2, and we find its value. So now, A2, we go now to this one. A2, x bar 2. So this one will be the area of this figure and also the centroid for this one. So this shape is a parabola. Parabola is 2 over 3 times base times height. So 2 over 3 times base, which is length, times 4, times h, which is 20, times the centroid for a parabola, either from left or right, is its length divided by 2. So it will be 4 over 2. So the answer will be 160.67, like that. After doing so, we can insert the known values into our formula. So we have MA L1 I1. So L1 I1 is 5 over 2 MA plus 2 MB into bracket 5 over 2 plus 4 over 1, because our L2 is 4, I2 is 1, plus MC L2 I2. So it is 4 over 1 MC should be equal to minus 6. On the right hand side, we will have negative 6 into bracket 140, which is A1 x bar 1, over L1 I1, which is 5 times 2, plus A2 x bar 2 is 160.67, over L2 I2, which is 4 times 1. Then we will simplify the equation. This one is 2.5 MB plus the whole of this is 13 MB plus 4 MC is equal to negative 325.005. So this is equation 2. We proceed again to the next two consecutive span. So we will have span, the final span will be span BC, CO2, like that. So we can write our formula using this. So we'll have MB L2 I2 plus 2 MC into bracket L2 I2 plus LO IO plus MO LO IO should be equal to minus 6 A 2 x bar 2 L2I2 plus A0 x bar 0 L0 I0, like that. So we are using MOLO and A0 x bar 0 because this side, it does not have any geometric figure as a result of maximum bending moment for free span. So we just use M0, L0, I0 like that. So again we say that, but LO is equal to IO is equal to A0 x bar 0 equal to 0. So we can eliminate some figures from this formula. So we will have MB L2 I2 plus 2 MC L2 I2. This one is 0. Again, this one is 0 is equal to minus 6 A2 x bar 2 L2 I2. This one is again 0. So this is our final formula. You can go ahead and find A2 x bar 2. So this one will be 2 over 3 times 4 times 20 times 4 over 2. So it will be 160.67. So it remains like this one, 160.67. After doing so, we can now put our known values into our formula. So this is our final formula. We can insert values in this formula, the known values. So we have L2I2, which is 4. Now let's insert our known values into these formulas here. So we have MB L2I2. L2I2 we know is 4 over 1. So it's 4 over 1 MB plus 2 times 4 over 1 again MC is equal to minus 6 into bracket 160.67 over 4 times 1. Close the bracket like that. After that, we will finalize by simplifying the equations of 5 MB plus 8 MC is equal to minus 160.005, like that. So this is equation 3. So we have 3 equations. So for this one, use a scientific calculator to find the values of MA, MB, and MC. So if we can arrange our 3 equations, we will have the first one as 5 MA plus 2.5 MB plus 0 MC, because I have added 0 MC because we did not have any value for MC. So it's 0 MC is equal to minus 96. And then the second one was 2.5 MA plus 13 MB plus 4 MC is equal to minus 325.005. Then we have the last one, 0 MA. Why 0? Because there was no value for MA. 0 MA plus 4 MB. This one plus 8 MC is equal to minus 160.005. So after doing so, you can punch this in your calculator and it will give you the values for MA, MB, and MC. So don't waste your time doing this mathematically because it will take much of your time and you need to save time. So punch direct in your calculator. So which imply MA is equal to MB is equal to MC is equal to. So MA is equal to negative 9.097 kilonewton meter. And then MB is negative 20.205. Then MC negative 9.898. Like that. After doing so, we will now calculate our reaction. And for us to do our reaction, we will split this continuous beam into a simply supported beam so that we can apply the three equations of static equilibrium to find reaction at A, reaction at B, and reaction at C. So let's do it. So split the beam. We have A. A is single joint. B we have to split B because it is a common joint. So we will have RB1 and RB2. And then we have RC. And this one is RA. So I have splitted RB because it's a common joint. So that is it. And then we have 20 kilonewton. This is 2 meters, 3 meters, 4 meters. At RB, we have moment, and that moment is 20.205. So you have calculated this one. At RC, we also have moment 9.898. 9.898. Again, at RA, we have moment that is 9.097, like that. And then we also have a UDL here of 10 kilonewton per meter. Now you can start calculating our reactions. So we know that summation, let's sum moment about a point. We begin with this section. So summation of moment about a point, which is RA, is equal to 0. So we will have minus 5 RB1 minus 5 RB1 plus 20.205, because this one is a moment and it is moving in clockwise direction. We come to 20, which is a pointing on which direction, plus 20 times 2, and then minus 9.097 equal to 0. Why? Because that one is a moment and it is moving in anti-clockwise direction, which imply RB1 is equal to, you can solve mathematically to find RB1. So RB1 is equal to 10.22 kilonewton. 10.22 kilonewton. If you have RB1, then automatically you can find RA. So RA is equal to 20 minus 10.22. Why? Summation of upward forces is equal to summation of downward forces. So the upward is RA plus RB1, and then the downward is 20. So automatically to find RA is 20 minus 10.22. So this one is equal to, RA is equal to 9.78. 9.78 kilonewton. We are done with this one. We go to this one. So let's sum moment about a point. So summation of moment at RB2 is equal to 0. So we have a force which is a reaction C moving anti-clockwise direction in reference to RB2. So that one will be minus 4 RC. Then we come to 9.89 in clockwise direction plus 9.898. We come to a UDL, clockwise direction again, plus 10 times 4 times 4 over 2. And then we come to 20, this one, in anti-clockwise direction, so minus 20.205 is equal to 0. Like that. So which imply RC is equal to, which imply RC is equal to 17.47 kilonewton. So what we need to find again is RB2. So RB2 is equal to 10 times 4 minus 17.47. Reason, summation of upward forces is equal to summation of downward forces. So upward forces is RB2 plus RC, and the downward is 10, which is a UDL. You multiply by 4 to make it a point load, so that is 10 times 4. So RB2 is equal to 22.53. So it's equal to 22.53 kilonewton. After doing so, our next thing to do is to draw a shear force diagram. So let's now see RA is equal to this one, 9.78 kilonewton. RB is equal to RB1 plus RB2. So this one will be RB1 10.22 plus 22.53. So this one is equal to 32.75 kilonewton. And then RC we have 17.47 kilonewton. Now let's draw our shear force diagram. So this one will be shear force diagram. So we have at A is 9.78. At A is 9, let's approximate, so 9.78. It will remain constant up to the next loading, which is 20. So you take 9.78 minus 20. So that one, it will give you negative 10.22. So negative 10.22. 10.22. Again, it will be constant. You add RB. So negative 10.22 plus 32.75. It will give you 22.53. 22.53. 22.53 minus 40. So that one will give you 17.47. 17.47. And then you join that. So negative 17.47 plus RC. 17.47 is 0. So it takes you back to 0, plus, minus, plus, minus. So we have now come up with our shear force diagram and its critical values. So these are the critical values like that. And the next thing to do is to go for a bending moment diagram. So you go to bending moment diagram. Before you draw a bending moment diagram, there is need to calculate a bending moment values. So bending moment. And before you calculate the bending moment, there is also need to have this point, because we will have our bending moment at that point. Let's call it y, and there is need to determine this distance. Let's call it, let's say this one is x, this one is 4 minus x. So find that distance first by saying that x, this one, over 17.47 is equal to 4 minus x over 22.53. This one is a similar triangle rule. So which imply x is equal to 1.75, which imply x is equal to 1.75 meter. So you can go further ahead and solve this. You will find x as 1.75 meters. So this is 1.75 meters. So the remaining one is 4 minus 1.75 meters, which is 2.25 meters. 2.25 meters, like that. So the next thing to do is to start calculating the values for bending moment. So bending moment at A is equal to negative 9.78 kilonewton meters. So you have, no. So bending moment at A is the value we calculated from our three equations. So that is negative 9.097 kilonewton meters. So bending moment at B, it will be bending moment at A, which is negative 9.097 plus the area of this one. So it will be 9.78 times 2. So it gives you 10.463. 10.463 kilonewton meter. So bending moment at, this was bending moment at D. Bending moment at B is equal to bending moment at D, which is 10.463 minus the area of this one. So minus 10.22 times 3. So this one will give you negative 20.197. The same value we obtain from our three equations. And then bending moment at y. Bending moment at y is bending moment at b, which is negative 20.197 plus the area of this one. So it will be 0.5 times 2.25 times 22.53. So this one will give you 5.15 kilonewton meter. Bending moment at C. At C, you already have bending moment at C. That one was 9.8. Negative 9.898. Like that. After doing so, we can now draw that is our baseline. So at A, you have 9.097. So we approximate along this line. So 9.097. And then at B, we have 10.463. It's positive, so 10.463. And then at B, 20.197. At B, 20.197. And then at Y, 5.12. At Y, 5.15. And then at C, 9.898. So 9.898. So this one will be a diagonal line like that. And then a diagonal also like that. This one is a curve. And also a curve. So we have minus, plus, minus, plus, minus. Like that. Again, we have another version of drawing a bending moment diagram. You can combine this one. You can combine this section. So we find MA as 9.097. So you will approximate along this line where A is and say 9. Let's say it's there, 9.097. 097. And then we proceed to MB, it is 20.2. So a little bit higher than this, so it will be 20.2, and then we have 9.89. So 9.89, and you will join this one, you'll join to this one, and then this one will join to this one. So this one will be minus, 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 plus, like that. So for me, I prefer this one because it's more professional than this one. So this one is when you are doing a rough work and maybe it's more of casual, this one. So in your exam, you can go for this one, but for professional, this one is the best. So that marks the end of that question, and you have scored our 20 marks correctly. So thank you for your time, and let's meet in my next session.